Okay, very welcome from my side also for today's presentation. I'm happy to talk a little bit about what I think where power electronics goes to. And to give a start on this one, let me first have a look what is the trend in power electronics. And Erik already introduced it a little bit. Actually, I'm very happy with power electronics because, well, what we can see is there will be much more power electronics in future because we have to replace all the fossil energies and it will be replaced by electricity. And if you just have a look how fast the development or the share of the renewables is in power generation and especially how fast it is rising, it is very impressive. We had the first terawatt installed in 2005, the second in 2015, the third in 2020, the fourth in 2023. And just to give an impression how many we need for full net zero, we need like 25 terawatts. And actually, I was a little bit surprised how fast we are approaching this and how fast things get better. And I just want to switch to the next slide. What we have to do to reach this goal is install worldwide 1.25 terawatts of generation capacity per year. And if we look what is currently installed, and this is already, the slide is some month old. I already now have the numbers for 2023. And in 2023, it was about 440 gigawatts of not solar, but renewable energy generation installed. And if you just look at this forecast, the forecast, even in the most optimistic assumption, was not as optimistic as reality is now. And if you just want to scale, if you just want to get an impression what we have to do, well, we only have to increase it by the factor of 2.5 and wait 20 years, and then we are with net zero. And when I researched for these numbers, I was quite surprised that we're getting so close and it's getting so fast and so accelerating. I think most people are not aware yet, and I have to admit I also was not aware how close we are coming right now. So, but this is, for power electronics, this is a nice thing because we know what we have to do. We don't have to, we will just have to handle the growth of our technology. This is more simple than having to handle a decline. Okay, let's get closer to translate this to what has to be done technically. And of course, the thing is we have to build a lot of these things we have to do. We have to build and we have to do it resource efficient. And we will have to build much more of it. So if we assume that we need 3 times more in generation, 3 times more power electronics in loads, the big question is how can we reduce the use of material resources? How can we increase efficiency? And how can we ensure highest volume and automated production? And how can we do recycling? Because unfortunately, our electronics won't survive much longer than 20 years. And hopefully it survives 20 years. And then we have to think about recycling. Okay, what to do? What are the solutions from the technical point of view? The first one is faster switching. This is the way we can reduce passive components and losses. So very strong, powerful way of improving power electronics. Then the other thing is more related to how can we reduce costs in production. And this is like the thing we have to already in the stage of development of the power electronics, we have to adapt what we're developing to the production requirements in order to minimize the production cost. And what we have to use for this is deep engineering knowledge And of course, I'm always very happy if I see what is possible today to do in virtual design and optimization in virtually. Many things we're doing nowadays we couldn't do when we wouldn't have simulation programs and stuff like this. I will give you, for all of these things in my presentation, I will give you some examples to get a good feeling. Okay, why or how to achieve faster switching or lower switching losses. Just to give a practical example, if you have an electric vehicle which has an inverter based on silicon carbide, and you drive the average drive cycle with this car, the inverter losses will be with 70%, it will be switching losses. So it's not mainly conduction losses, it's mainly switching losses. So gives an idea why faster switching with less losses makes very much sense, even in a drive inverter. And we have a long history of optimizing power modules for better electromagnetic properties in order to switch as fast. And you can see here in these slides, we put together the switching waveforms of different modules we built. And the light blue one is actually the best one in the end after many generations of optimization. So we can switch as fast as the semiconductors allow it without any ringing, without any, with a very steep slope. And that gives an impression how you can significantly reduce switching losses. And speaking about the drive inverter and the electric vehicle, it would be easy to reduce the switching losses by half compared to what is on the market today. We started these activities on optimizing switching cells for power semiconductors already long ago, and this is, I call it generation 1. It was the ultra-low inductance package where we already achieved DC link inductance of 600 picohenry and used a technology that is somehow implemented in very many generations. Just to give an impression, we're now building generation 26 of power modules. But it is, many of them follow the same way of building. We have here, you see like how it's built up. We have a ceramic substrate for good thermal performance. We placed 4 silicon carbide semiconductors already 10 years ago. And then we laminated on top like a printed circuit board structure. So we use printed circuit board technologies, and thereby we could achieve these electromagnetic very positive properties. And here you see the cross section of what is inside. The gray thing here is the semiconductors. You see the microvias contacting the top side of the semiconductors. And unfortunately, you don't really see the printed circuit board material here in between and here in between. This is the lamination process with the ceramic down here. And the reason, or let's say, there were many ways of optimizing it. We did the next generation where we also improved the EMI behavior. And you see the production process here. We have ceramic substrate, silver pads metallized onto the ceramic substrate. Then we placed semiconductors, silicon carbide semiconductors onto it. In this case, it was one regular, one was flip chipped. You see here the detail of the flip chip with the insulation material. And then we started building a printed circuit board. I don't have photos on that one, but in the end, it looks like a printed circuit board, but there's the ceramic inside and the this semiconductors also. You see here some DC link snubbers and some driver parts. And thereby we can achieve, by this technology, we can achieve both best thermal performance by using the ceramic substrates and electromagnetically best performance by using the printed circuit board technologies. Fortunately, we're not the only ones. So the industry now adapts, let's say, first the low inductance technology. So I was very happy to see, for example, with Semicron in this case, creating a package with a low DC link, low inductance DC link connection, which you see here. And inside, in a different technology, they used like this flex foil to achieve the low inductance inside, but it came up to a pretty similar result, like 2.5 nanohenry. So this is available on the market, and what I see with the embedding technology, it really took like 10 years. But if I see now how many companies are implementing embedding technologies with silicon carbide now and coming to the market soon, it is very interesting to see how long you need from the first idea till it really enters in the market in this area, which is well, the industry is a little bit conservative at that point. Okay, so that was some very short idea on how high power, or let's say high performance power modules can look like. These were the first ones. I have another presentation where I can show all the different types of power modules we built, but there's two directions we're working on. The first one is making good use of the semiconductors. The other one I want to now focus on is how to make things cheap and easy to assemble and complying with regular technologies. And we recently see more activities in topside cooled SMD packages. And this is something that very much makes sense. And I want to show some examples on what we build with these topside cooled, or how electronics can look like with them. We also started these activities, and we went a little bit further with the topside cooled, because we also always integrated some insulation for these modules. So you see, we just used a in this case Gun Systems topside cooled package. We soldered it to a little ceramic substrate. You see here the X-ray of the soldering. Fixed it with some glue, and then soldered it to a printed circuit board as SMD components, like regular SMD components. And you also see the underfill here, which is needed for the insulation. And this gives us an impression. It's like only 1.4 millimeters in thickness. And then you have a component which is very well cooled, which you can press onto a heatsink, and which already provides the full insulation. And by a ceramic, it's also high performance insulation. Yes, some things have to be solved if you do so. The question is mainly how good is the thermal contact, and we did a measurement here, what the tilt of the components is, how well they are pressed to the heatsink. And you see there are some difference. They're not perfectly even, but the main issue we had was actually the bow of the printed circuit board itself. So the components were relatively flat, but the bow of the printed circuit board was the main issue here. Yes, but you see here the mounting screws, they press the printed circuit board to the heatsink. Okay, so what are the consequences? We have two approaches leading in the opposite direction. We have a high level of heterogeneous integration to maximize the performance. It is like you can integrate many functions into a power module. And the other direction is high flexibility by adapting standard packaging technologies for power electronics. It's more low-cost approach. And yes, if someone designs something like this, you have to need a little expert knowledge. But both have their direction, and I think both will go their way in high volume production. Okay, so let's come to the technologies that can be used. I talked about how can packaging look like. Now let's come a little bit more closer to the technologies. And you already saw I pretty much like the printed circuit board technologies to be used as one packaging technology. I will also focus on the other one we use, the transfer mold or the compression mold. What is the advantage? Well, this is a very established production method, and the lot size for this production method is like 60 times 60 centimeters in a printed circuit board. And if you package chips in this technology in such a size and a lot size, you can put a lot of semiconductors in one of this package. And this is, of course, something that reduces production costs, because you have every production step is then divided by a lot of semiconductors you have inside this panel. And that makes things cheap, and that's actually what we need for high volume production. We need production methods like this to cut down cost. What is the process? I mentioned in the beginning that we, in the very early stage, combine ceramic substrates with printed circuit board technologies. And I just want to give you a sketch how it works, how we do it here. You see here in the middle, we have a ceramic substrate, an A and B, mostly for silicon carbide to get the best thermal performance. We combine this, or we manufacture this to get a printed circuit board panel by putting some core, some prepreg material, laminating. Then we have like a printed circuit board panel with ceramic substrates inside. In the next step, we place silicon carbide chips onto the ceramic substrate. We mostly sinter them, silver sinter them, as we want to have the highest performance. Then we put another layer of prepreg, or two layers of prepreg. One is with the cavities for the semiconductors, one is going through some copper. On top of it, that's laminated here. And then we take the laser drill, drill the holes, and the vias, and do metallization. And that's actually the process of this ceramic in printed circuit board. Okay, so this is one way. We have many advantages. The production methods are very well established. Equipment is available in many places, and also the technical maturity of the materials available is very high. So you get a very high selection of materials you can use for this. And I can tell you, when we embed silicon carbide chips, we don't take the cheapest material, because this is a very critical component, and you cannot take like the most cheap printed circuit board material that won't withstand the electric fields, and the will not have the lifetime. We have some waste in raw materials. So you see, if we cut out printed circuit, here the ceramics, for example, we throw away a lot of material. Here for the chips, it's not so much, but it is some things we have to think about when we go for high volume. We also have to think about how much raw material are we using and how can we reduce it. Another way that avoids this issue is compression molding, and compression molding is actually a technology that comes from the chip manufacturing. In our institute, we scaled this up to also have possibilities to produce much bigger. So normally in compression molding, you have like round wafers, and we developed together with a machine manufacturer a machine that is able to produce big lots like this. And yes, we has some, it is very promising. We can also produce, we have similar scaling effects like with the printed circuit boards. It is much bigger compared to compression mold, which is also a very common technology. So it's something we're driving forward, and I think it makes very much sense. And we're also scaling up this to higher thicknesses, which is necessary for the power electronics. Yes, this is just the process. You have some carrier where you have the things you want to mold, maybe put ceramic substrates with chips on it. you have some epoxy mold, then you press this together and the cavities is filled. You don't have any, or you have much less wasted material. So this can be something that can also be very interesting for large volume production. Yes, I mentioned this already. The technology comes from the chip manufacturing. That's why it was wafer size. And now we scaled this up to packaging size. Okay, we would use these technologies, for example, to build pre-packages. Pre-packages you see here is inside a printed circuit board already, in this case with a semiconductor, with a ceramic substrate and some black mold around it and some contacts. You can put pre-packages like this into a printed circuit board, or in the way I showed it in the other slides, you can put it on top of the printed circuit board. And from my experience, this version is more common, makes more sense, because as power electronic people, we always have a lot of current, and a lot of current needs a lot of copper. And so we use the volume in the printed circuit board as for the copper and not for the semiconductors. They can sit outside. And if we continue this, so if we build like inverters like this, we can also think, how can we build power electronic devices which make use of this? And if you put these things together, if you are aware of like topside cooled semiconductors or pre-packages, which you solder onto a printed circuit board, and then you also use the printed circuit board for integrating the magnetics, using the printed circuit board windings for the magnetics, you get things, power electronics get really flat on the one hand. On the other hand, you can use automated production methods to build them and not have any hand-wound inductors anymore, which are, let's say, bulky and you have a hard time cooling them. So this is a strategy we're following, and we're building, we're not building anymore, we built already a 22 kilowatt onboard charger. And I want to give you some ideas what components we're using there. And the one thing we're doing for this onboard charger is a 1 megahertz DC-DC converter with 11 kV. And you see how it looks like here with a core with 4 legs and the windings inside, which inside the printed circuit board, which handle the currents. And it's also operating here. You see it gets hot. Well, that's what it should do. And it's very interesting because it works at 1 megahertz, and it is, of course, pretty much a challenge to get something operating at that frequency and that power. And it took us quite a while to get rid of all the, let's say, beginning issues, or let's say ramp up issues. And one thing we had to find out is a way to optimize our layouts in order to minimize ohmic losses due to skin and proximity effects, which if you do it wrong in such an application, you have a nightmare. It is like it's you will never get it working, and it is not intuitively that you could optimize your design. So the first step was to develop the methodology to efficiently simulate the layouts we create in finite element investigations. And you see, after building the first transformer and it didn't have a good efficiency, we checked it, and then the first thing was we have some resonance inductivity here in the layout, and you see this resonance inductivity is burning. Like this was the first mistake. That was not possible. So we started virtually optimizing the designs, identifying what is the weak point, changing the layout, finding another solution, resimulating. And I just will pick out some of them. In the 7th design, we started symmetrizing resonance capacitors, increasing insulation layer thickness for more stray inductance. You see, we build up here there's one layer here, the 500 micrometer layers. This is really, in this 500 micrometer layers. This is the stray inductance. We use the 500 millimeters different distance between the layers to create our stray inductance, and then it doesn't have the losses it has here. It goes on and goes on. When the 9th design, we found out that the different layers, we have some parallel layers, had very different losses. So there was one that had lots of losses, and the parallel one, although it was directly connected parallel, had very little losses. And continuing this, we analyzed the layer stack up, and we found one position in the layer stack up where we had like one return current, the red one here, and many currents in the other direction. And then the skin effect cancellation we normally use in this transformers didn't work anymore. And then we got a very unbalanced current share in the layers, and that was created lots of extra losses we cannot afford. And then we optimized the way the routing was done, distributing the currents more evenly in the layer stack up. So that worked out. So we see still some differences, but much better now. But if you look in the simulation, you see how the vias are burning. They are still creating a lot of losses, so there's still some things to be improved. But at that point, we more or less stopped because we had to get the thing manufactured, and we accepted the extra losses in the vias. Okay, that was for the transformer. For the PFC, we followed a similar concept. We designed inductors, which are also flat, which have PCB windings. And just to give an impression, this inductor here has handles the 32 amps for the PFC. It is like the ferrite is 75 times 75 millimeters, and it's 13 millimeters high. And we use a coupled inductor strategy to cancel skin effects and get this thing running. Again, following the strategy, we have to design the magnetics in a way that it fits to automated production. Oops. So, okay, the total onboard charger, which has like 3 liters, this is still a construction picture. I can now also add the real life photos where we have 3 PFC chokes, 2 DC-DC converters, some DC link and power modules in this case, and a big EMI filter. And that's what we are now bringing into operation, and most of it is already working properly. The control is not fully finished, but working on it heavily. But it gives an impression how power electronics can look like if you follow this strategy I showed, like how can we make the components, or how can we develop already at the topology stage the system in a way that that you make use of possibility, or that you consider how production can happen, what is favorable in terms of production later on, and thereby reduce cost heavily. Okay, to come to a conclusion, what we're trying to do with our designs is to reduce material use, as we have to produce a lot of them, and the less material we use, the better. This complies with the limited resources on this earth. And at the same time, of course, we have to be cost competitive, and that's also comes along. If you need less resources, it is also very, it's also in the end cost effective. If we incorporate the production processes already in the stage of topology decisions, it is the key to achieve these goals. And what we also think is that the higher production numbers will enable deeper engineering for better performance in all directions. But what I'm facing already personally is a lack of skilled engineers we even, of course, as an institute, we're also educating the people, but even finding enough students is already hard. So this will be a limitation we are facing, and probably many others are also facing. Okay, many thanks for your attention. Any questions?